Okay, thank you, Hannah, and hello, everyone, and welcome to a discussion of battery technologies. This is going to be kind of an overview of the different battery technologies that are available to us in the solar energy world at this time. I'm not going to get too far into experimental technologies that may be in labs at the moment, but just what is actually on the market and available to us. So we have a short period of time for this. I want to leave as much time as possible for questions. So I'm going to kind of jump right into this, get going. So hopefully everyone can hear me okay and see the screen okay, and let us know if you have any problems. First, I want to have a disclaimer that AEE Solar is a distributor of goods and services. We're not accountants, attorneys, or code-making experts. The information we're presenting for the equipment rules and best practices that we're aware of. However, local and project-specific requirements can vary widely, so keep that in mind, please. Okay, we're going to jump right into flooded lead-acid batteries, which are one of the oldest battery technologies available to us, and it's been pretty much a mainstay of renewable energy systems, particularly off-grid systems, for decades, and very commonly used in off-grid applications. Rarely used in backup systems, mostly because they require a lot of maintenance, and they do require some charging and discharge cycles to maintain their health. And that's generally not too much in backup systems. So these are really used more for full off-grid systems. The VRLA batteries, which are valve-regulated lead-acid, and I'll get into that next. They're available in all kinds of sizes, from very small ones to very large ones. They have excellent cycle life. Electrolyte loss is replaceable. Generally over time you lose some water out of the system. It is a acid-water mix, so the water is lost. It is replaceable though, because of open design. And they're less sensitive to overcharging, mostly because of that reason. If you overcharge them, it just bubbles off some of the water, which is replaceable. Now, constant overcharging can damage them, so you don't want to have something that's always overcharging the batteries, but they are less sensitive to occasional overcharging. Cons of them are that they're not sealed, so they can't be mounted on their side, can't be shipped by air freight. They need to be isolated and ventilated. They do release both flammable and toxic gases, so you need to ventilate them out of a room. They're not a good thing to have in a living quarters. You want to have some sort of special place for them. They do require maintenance. Water must be added. They should at least be checked monthly. When the batteries are new, they probably wouldn't require water monthly, but as they age, they're going to use more and more water, so you have to be aware of that. They do require regular equalization charges, which is a controlled overcharge, mostly to mix up electrolyte. You have a mix of acid and water in the battery, and especially with a tall battery, such as the ones pictured here. As they sit, they tend to stratify, where the acid, being heavier than the water, will settle to the bottom of the battery. Water will float to the top, and you need to mix those up. So we do that bubbling the batteries, and that's usually done through a controlled overcharge called equalization. Equalization will also even out the voltages of the individual battery cells. Each cell of a lead-acid battery is 2 volts. But over time, some cells become a little weaker than others, and keep them all level again for a period of time and letting them bubble and fill up completely. They are less efficient in some ways. They have a higher self-discharge. Generally not a problem in systems that are charged and discharged every day. Higher self-discharge is really only a problem if a battery is sitting for a long period of time. They do have a higher float current, so you do have to put some float current to them on occasion, and that can equal some energy that's just required for the battery maintenance and not actually used for the system. They're somewhat sensitive to shock and vibration. Generally not a problem in a stationary application, and they seem to work just fine in automobiles, so they're not super sensitive, but because of their design, they are somewhat sensitive to shock and vibration. This is just a photograph of one particular lead-acid setup. This is a Solar One 24-volt setup. Each stack is 12 volts, and I just wanted to point out here the custom-made on-site battery enclosure. Entry place on the left side, and that conduit is sealed to prevent gases from going up that conduit and into the power system. And then on the right side back of the box, there's a vent which should exit the building to release hydrogen gas and other products of the charging process. Very important to do that with lead-acid batteries that are flooded. Then the next step in lead-acid batteries is what we call gel cell valve-regulated lead-acid. And in this case, instead of having a liquid electrolyte, it has a lead-acid electrolyte that's in a jellied kind of form between the lead plates in the battery. Excuse me. And so that it's more of a kind of a captive electrolyte. The pros of that is much lower maintenance. You don't have to do equalization charges because the electrolyte is not going to stratify since it's bound up in a jellied form. They're sealed, so they can be installed on their side. They can also be shipped by air in most cases. They have very good cycle life. We typically recommend gel cell battery for small stationary applications such as traffic signaling or railroad signaling.
Brian, can I interrupt you for a second? Your audio is kind of breaking up. Is there a way to maybe bring the mic a little closer?
Well, we're in a voice over IP system, so that's an internet glitch of some sort. There's not much I can do about that.
Okay. It's not too bad, so we'll just keep going.
Okay, yeah, sorry about that, folks. I'm doing this from an off-grid house, and it's a radio link, so sometimes there's glitches in it. Anyway, get back to it. They have a very good side for sealed batteries. They are high efficiency. They do have very low self-discharge and float current requirements. They are shock and vibration resistant, again, because of the jellied nature of the electrolyte. However, because they are sealed and in a mobile form of electrolyte, they can be easily damaged by overcharging. So you have to have very good charge regulation, including temperature compensation on the charging source. If you're going to put them out in a box in the sun in Phoenix, they're not going to last real long. So they do need to be kept at a lower temperature. They do have lower charge and discharge rates than AGM batteries. It's a more immobilized type of electrolyte, so the chemical reaction happens a little bit slower. Generally not a problem for most systems these are used in. They do have a slightly higher cost than typical AGM batteries, but again, their cycle life is typically higher, so it usually makes up the difference. And lower capacity units are available than flooded cell or AGM. You can get very small batteries in these for very small applications. The next type of battery is what we call an absorbed glass mat valve-regulated lead acid, or an AGM battery. These are becoming more and more popular as the quality of them gets better. Again, they're very low maintenance. They're sealed, so no electrolyte levels have to be checked. They can be installed on the side and usually shipped by air. They are very high efficiency, self-discharge, similar to the gel cells, and shock and vibration resistance, again, similar to gel cells. And these work also very well in high power applications because they can have very high charge and discharge rates available to them. And you can get them in very large capacity battery cells, some of them even up to like 6,000 amp hours. So it's possible to get very large batteries in this kind of form. Just like gels, they are sensitive to overcharging. Same idea is that because they're sealed, there's no way for gases produced by the charging process to escape. And if they do escape, you can't put it back into the battery. So they are sensitive to that overcharging problem. They do also have reduced life at higher temperatures. The electrolyte cannot be replaced. So again, if anything were to escape through the valve system, you can't put it back in. So it needs good charge regulation and temperature compensation. They do have higher initial costs and small sizes than flooded batteries, but considering free and smaller compartments that don't need as much ventilation, they still should be vented in case there is some release of gases, but they don't require as much ventilation as flooded batteries. Here's a couple of examples of larger systems. the Deca Unity 2 AGMs and the Outback Energy Cell AGMs, both excellent batteries. The Deca Unities are really designed for backup systems. They don't have a high rated cycle life, but it lasts for many years in backup systems. The Outback Energy Cells are rated to 1,800 cycles, 50% depth of discharge, which is excellent cycle life for a sealed battery. Then we're going to take a look at lead-acid batteries with carbon. This is somewhat of a new technology that there's a couple companies, Trojan and Outback in particular, that have formulated a new lead-acid battery that has some carbon in it. Carbon is added to the negative state of batteries. And what the carbon does is it prevents the formation of sulfide crystals, or at least it reduces the formation of sulfide crystals, which improves the partial state of charge performance. One of the things that lead-acid batteries do, if they're left in a partial state of charge for extended period of time, is you get crystalline sulfide built up on the plates, and as they, the longer they're there, the harder they become, and it becomes harder to redissolve back into the electrolyte and effectively removes capacity from the battery. So by adding a little carbon to the negative plate, it helps prevent the formation of these sulfide crystals, which means that the batteries can remain in partial states of charge for much longer without any damage. This could be really helpful for off-grid applications that are either areas that have extended cloudy periods or just in situations where they're not charged up fully every day or even on a regular basis. So they have an extended partial state of charge capability. There's less need for full charges. Because they're sealed, you don't need to do equal charges either. Excellent, for self-consumption in off-grid systems. However, there's no real advantage to standby backup systems because of this, because backup systems are typically not left in partial states of charge for periods of time. They're just meant to take you over a temporary lapse of power from the grid, for instance. They do have a longer cycle life in real conditions. According to manufacturers, you can get up to 44% improvement in cycle life from them with only a 15% higher price. So they appear to be very cost effective from that standpoint. They are available in sealed AGM form or flooded batteries. The Outback Energy Cell Nanos are what you see in the upper left column, and the Trojan Smart Carbon commercial and industrial batteries are in the lower right there, the red ones there. So you can get them either sealed or flooded. It's a very interesting new technology. We don't have enough of them in the field for enough years to really assess what they're doing in the field, but they appear to be a major improvement in lead acid. Now here's a new technology that's just come forth in recent years called an Aqueous hybrid ion, made by a company called Aquion at the moment. I assume there may be more companies adopting this technology. It's basically a saltwater battery. It uses sodium salt in it and other components. A little bit of lithium is in there, a few things, but all non-toxic materials. They have very high cycle life. As we show here, 3,000 cycles to 100% depth of discharge, 6,000 cycles to 50% depth of discharge. Now you'll notice from that, whatever the amount of discharge is, depending on the size of the battery, that if you do 3,000 at 100% or 6,000 at 50%, so it's really the same amount of kilowatt hours delivered over that. If only about 20%, something like 10,000 cycles. Cycles. So this could be a very long-lasting battery. Can operate in a pretty broad temperature range, although not very cold, below 5 degrees centigrade or 23 degrees Fahrenheit. They don't operate very well full life. They're durable and very abuse tolerant, completely tolerant of partial state of charge. Parallel strings are self-balancing. I didn't really go with that with lead acid, but with lead acid batteries, you really don't want to have more than like 3 parallel strings because you end up with inefficiencies in charging each string equally, and you end up with imbalances among the battery bank. That's not really a problem with the Aquions. They're really self-balancing with parallel strings. They can be completely depleted down to 100% without any harm to the battery, although as you can see from above that it does reduce the number of cycles that you have available if you do that on a regular basis. There's no active management necessary in small systems. When you get into much larger high-voltage systems, you have active management. But 48-volt and lower systems, actually they're only available in 48-volt right now. Although I understand they're working on a 24-volt product. They're very safe. There's limited power output to shorts. Each one, if you look at the picture there, that's what's called a module that consists of 12 battery stacks. Each stack has a maximum output of 17 amps. So you can actually short circuit a stack and only get a maximum of 17 amps. It's very short circuit tolerant in terms of safety. They won't support any kind of flame. There are plastic cases, but other than that, there's no other flammable materials. They won't explode, or there's no thermal runaway issues. They're all made of non-toxic materials: sodium, a little lithium, salt water, electrolyte. Very simple materials that can actually be easily recycled. You can actually just, when the battery life is done, you can just bury those materials without a problem. They are still moderately expensive, 2 to 3 times the price of lead acid batteries. Now, if you go to the very high end of lead acid batteries, like for instance the AEE Solar ones, they're fairly competitive in price there. But for a lot of commercial or even other industrial batteries, these Aquion batteries are a bit more expensive. But of course, their advantages may completely offset that extra cost. They do have low power and energy density, so it requires more space for the same amount of capacity. They have a very wide voltage range. They're rated from 40 volts up to 57 volts. So actually at the very low end of the spectrum, that's typically outside what most inverters can do, but that's only really the last maybe 10% of its capacity goes below about 44 volts. So fully usable with the equipment that's available on the market. They have low rates of charge and discharge. Again, 17 amps maximum per stack. So you can only charge or discharge at the maximum, and really 15 amps is really what should be aimed at for each stack. And if you have 12 stacks, of course, that's up. So you get enough voltage and enough charging capacity with more stacks. They do have a limited capacity at higher rates of charge and discharge for that reason. They are pretty heavy. Each stack is 260 pounds. That module, as you see in the picture there, is 3,300 pounds. So they are pretty heavy. It is, the stacks are modular, so you can move them per stack, but that's still, quite a lot of weight. Here's an example of a bunch of stacks here. That's actually 10 stacks in there, which means that it would have a high capacity of 170 amps, either charge or discharge. Or 150 amp if you want to have a little safety level there. It's just one level there. It's not releasing any flammable gases, so you don't really need to have it in a special container or vented. And you don't really have to worry about an acid spill either. It's all non-toxic. This is an example of their modules, which are their prepackaged 12-stack systems. 3 of them in the picture. And you can parallel a few of them. I don't know off the top of my head the total number, but you can get to quite a few. And they're developing these also for utility scale storage. Next thing we'll talk about is the Tesla Powerwall, which is a lithium, nickel, manganese, cobalt oxide battery. Kind of new on the market. They're just starting to be installed now in places. I think the equipment that goes with them is still somewhat experimental. It's still being developed as a system. But this is going to be a very high voltage battery. It typically operates in the 300 to 400 volt DC range. So it's all plug and play at that point, no exposed terminals. Very interesting technology. They originally came out with 2 versions, but they have dropped the 10 kilowatt hour version and now are just down to the 7 kilowatt hour version, which is actually 6.4 kilowatts of usable energy. It is high voltage, which substantially reduces current and wire sizing. Take a look at it does require that you have wall space to hang them on. They have very high cycle life at high cycle depth, up to 3,000 cycles at 100% depth of discharge. There's a high round-trip efficiency, very efficient design. The control of thermal issues, they are liquid cooled. They have a whole cooling system in them and a whole battery management system built in. They can be used from temperatures between -20 centigrade and 50 degrees centigrade because of the internal cooling and heating. They actually maintain a set temperature. Easy to install, well, I'm not sure about that. Lightweight, they still weigh over 200 pounds, about 220 pounds, which is quite a bit of weight to lift up and put up on a wall bracket. But you know, a couple of guys and a lifting hook maybe, and it could certainly be done. It will integrate with solar inverters that are designed for this kind of high voltage input. Right now, Solar Edge has a product that works with it quite well. It fits into their 300 volt DC bus that they use with their optimizers. But other companies are coming out with other technology to work with these batteries. They are lightweight and touch safe. It's rated for outdoor use, so it doesn't have to be inside a sealed area. Multiple units for higher capacities, up to 7 units. Tesla's still working on the infrastructure to do that, but they see no reason why you can't use multiple of these units to get more capacity. Cover design are available in different colors. If your customer wants a particular color, it can be done on these batteries. They are pretty expensive compared to lead-acid batteries. Right now, they're rated for a 10-year life. Again, none of them have been out for anywhere near that time, so we don't have any long-term analysis of that, but that's what the company is claiming is a 10-year life. Installers have to complete a special training course with Tesla to be able to install these. Right now, they're limited to 1 or 2 parallel units, but again, that will expand later. And lithium inverter, I mean, with any 48-volt based inverters, it has to be high voltage DC input. So all the inverter companies are working on inverter systems that will match up with this kind of battery technology. And Tesla's not the only one working in this range. Mercedes-Benz has also released in Europe a stationary battery. I think, you know, trying to compete with Tesla, not just on the automotive front, but also on the battery front. And I'm sure we're going to see others coming around. And here's kind of a picture. It's probably photoshopped, but you know, this gives you an idea that it can be mounted outside on the side of a building and just be you know, wired in through conduit into an internal section where the inverters would be. You see solar on the roof there. So you know, it's not a whole lot of backup power with a single unit. You know, roughly 6 to 7 kilowatt hours. But it could get most people through short-term utility outages and could be very useful for that purpose. So there are other types of lithium-ion technology. There are many different types out there. These are widely used in laptops, electric vehicles, handheld devices. I'm sure all of you are somewhat familiar with some of the lithium-ion batteries that are available. They do have very high power and high energy density, which is one of the reasons they're used in portable devices so much. Discharge rates are very high, and they have a very high watt-hour per pound ratio. Again, a great reason why they're used in mobile applications. And they have very high cycle life, rated up to 3,000 cycles at 80 to 90% depth of discharge. Got a couple pictures here, some typical setups. They're still very expensive, 2 to 5 times the price of lead-acid batteries. So, you know, all these new technologies are coming in more expensive than lead-acid right now, but I'm sure that in the future we're going to see improvement in manufacturing and higher volume, which is going to bring these prices down and make them a lot more competitive with lead-acid. Again, rated at a 10-year limited calendar life. They do have thermal challenges. Typically, they do need thermal management units, electronic units that control their charging and discharging. There's some risk of thermal runaway. However, what seems to be settling out as the most common form of these batteries is the lithium ion phosphate, or LiFePO4s. And these chemistries are less prone to thermal runaway risk, but are more expensive and have slightly less energy density. So there's trade-offs. You can have lithium technology that have very high densities, but are not necessarily very safe. And so there's a trade-off in having the energy density go down, but have a safety factor go up. And lithium iron phosphate seems to be the technology that's making the most improvements in these fields. Again, they do require some sophisticated battery management systems, which adds to the cost of the batteries, but it's typically quoted as part of a battery quote. And they're non-recyclable and hazardous at this time. Again, as more are in the field, there will be ways of recycling them. There's no reason why the materials couldn't be recycled. Disposal or recycling costs are typically not included in the price. Whereas lead-acid batteries, you may be familiar with having core charges. You can always turn them in for recycling. They're actually quite valuable for recycling. At this point, there's some shipping restrictions on some of them. And they will support combustion in a fire, and this is something that is being looked at by a lot of fire officials and fire regulations as to where they're going to allow them for installation in houses, for instance. They may not be a fire risk in themselves, but how they react in a fire that may have started for some other reason at some other location in the structure. This is something to consider as to how they'll do that. You'd have to make sure you're working with your local fire department and make sure you're up to the codes on that. One final technology I'll talk about here is nickel-based batteries. They're either nickel cadmium, nickel iron, or nickel metal hydride. There's a bunch of pros and cons to these two. They have very good energy and power density, although only about 60% of lithium ion typically. They have very high cycle life at high cycle depth. Some of the larger industrial cells are rated for up to 11,000 cycles or more at 80% depth of discharge. Many of these nickel iron batteries were used in rural electrification systems back in the 1930s, and they lasted for decades. And there may even still be some out there working as far as I know, but they have a very long life. Are rated typically up to 5,000 cycles in a flooded form of NiCad. NiCad batteries are kind of falling out of favor these days, mostly because cadmium is a very toxic material, and so recycling is very expensive, and that adds so much to their cost that NiCads are not really produced in very large quantities. More nickel iron hydride. They're very robust designs. They're not prone to sudden failures like some other types of battery systems. They're very tolerant to under and overcharging. Have a very wide operating range. Whole bunch of advantages here. They have very flat voltage versus state of charge curve, which is good for running equipment because your voltage is not falling or rising all over the place. It makes it a little harder to determine the state of charge on the battery. You pretty much need an amp-hour meter that's counting amp hours in and amp hours out to be able to really read the charge capacity of the battery. And they are generally made of less hazardous materials, again, except for the NiCads, because cadmium is pretty toxic. They're very expensive. They do contain heavy metals. Even nickel is a heavy metal. It's not as physically dangerous to the body as cadmium is, but it's still a heavy metal. They do have lower cell voltage, typically 1.2 volts per cell. So a 12-volt system would require 10 cells instead of 6 cells, which you have with the lead-acid battery, since those are 2 volts a cell. So you do require more cells in the system. There's some advantage to that. It also gives you a leeway to have one more or one less cell without having a whole lot of difference in the whole system voltage. So if one were to fail for some reason, it could be removed from the system and you still have a functional battery system. They do have a high self-discharge rate. So these wouldn't be a good idea for backup systems or systems that are only periodically charged and need to maintain their charge rate. They're better in systems that have some charging almost every day. NiCad cells have a memory effect in the sealed cells. Nickel metal hydride, which is the other sealed cell technology, don't have as much of a memory effect, but there's still a little bit of it there. They should be discharged and recharged fully on a more regular basis. It does have an alkaline electrolyte rather than an acidic electrolyte. So if you're electrolytes, you need to do have an acidic material such as vinegar. So you're adding one liquid to another. It's a little messier in the cleanup than adding, say, baking soda to sulfuric acid, which tends to be something that's more easily cleaned up. And these, in the flooded form, these require electrolyte changes. Now, the electrolyte is an alkaline electrolyte, but it's sensitive to carbon pollution from CO2 in the air. So over time, the electrolyte will absorb enough CO2 as to become less and less effective over time. It might be anywhere between 5 and 10 year period typically. The electrolyte does have to be changed in it. That's kind of a messy process, but you have to wear protective clothes and whatnot, but it's not impossible to do. And basically, once you put the new electrolyte in, you basically have a new battery at that point. It really revitalizes the battery. So that's an advantage of sorts, but it is something that has to be done. It's amazing. So here's I just have a photograph here of a large nickel iron battery bank and 2 outback radiant inverters on the wall there. So they are available in pretty large systems. It's really, proper care, it's really a lifetime battery. So I'm going to jump into the questions here, but before I do, I want to mention that there are, of course, other technologies. There are batteries called flow batteries, for instance, that have external tanks of electrolyte, 2 different electrolytes that are mixed through a central unit, kind of like a fuel cell, that produces electricity, and then that liquid can be recharged into its original form. There are other types of very small batteries that are being worked on, more on a carbon base than a lead base, but none of those technologies are really available on the market yet for use by us, so I didn't cover them in more detail here. So anyway, I'd be glad to take any questions that you have, and hopefully I can answer them all.
Great, thank you, Brian. If anyone has questions, feel free to submit them through that questions box. We've already had quite a few come in during the presentation, so we'll get started on those. But before we do, I just want to remind everyone to complete the survey. It'll pop up after you exit the webinar and will also be sent in a reminder email an hour after the webinar ends. Complete the quick webinar and I'll send you your NAPCET certification, a copy of the presentation, and also a webinar-only special that you won't want to miss, so don't forget to do that. I'll also be uploading this presentation to YouTube, to our YouTube channel, AEE Solar, after the presentation, so if you missed part of it or got in a little late, feel free to go back and watch. All right, so we'll get started here with a few questions. First question we have, do you think a taller battery stratifies more than a shorter battery?
Yes, definitely. There's just more place for it to stratify. And even a shorter battery will stratify, but it just becomes more of a problem as the cell gets taller. You get higher concentrations of acid at the bottom, lower concentrations of acid at the top. Of course, the higher concentration of acid is not only removing that acid from the top part of the plates, but it also can be corrosive to the plates at the bottom. And that is a bigger problem with taller batteries.
All right, our next question. For the lead-acid battery, sealed battery with the carbon technology, why is sulfication still a factor?
Well, what they say is that it reduces sulfation. It doesn't say it eliminates sulfation. So I suspect that there was just some sort of, again, I'm not a battery chemist, so I can't answer specifically, but I suspect that it had to do with some sort of trade-off, that if they added more and more carbon, that they had some sort of lesser yield of capacity or life or maybe ruggedness of the battery. I'm not really sure why they did that, but they got to the point where they could have some lead in, some carbon in there, and it had some effect. Wasn't able to make cultivation.
All right. The next question we have, for the Tesla 6.4 kilowatt, at what rating do they take this if I want to convert that to amp hours for a 48-volt DC system?
Well, you have kilowatt hours, so that's 6,400 watt hours, 6.4 kilowatt hours. So if you convert it to watts, to 6,400 watt hours, and divide that by 48, you're going to get your amp hour capacity as an equivalent. Now, because of lead-acid batteries, really the last 20% of the rated battery capacity is not really useful, whereas with lithium, you can take them down lower, although it has built-in devices to prevent you from overcharging the battery. There's not necessarily an exact comparison, but it's going to be pretty close. By just converting kilowatt hours to watt hours divided by the voltage that you use, you'll get the amp hour equivalent.
All right, and a question about Aquion. How many amp hours are in each stack?
That's a good question. I don't know off the top of my head. I can maybe look in the catalog here. I think it's like 52 or something like that. The 12 stack in the module is something around 560 amp hours of rated capacity. But again, you can take it down 100%. So, a 560 amp hour Aquion battery is probably equivalent to about 700 amp hour lead acid battery in terms of actual usable energy.
Okay. And then what's the equation for figuring net usable kilowatt hours from amp hour rating? Oh, Brian, are you there?
Repeat that question? Yeah, sorry, I had a little glitch here. Can you repeat that question?
Oh, of course. What is the equation for figuring net usable kilowatt hours from amp hour rating?
Okay, if you're dealing with a lead acid battery, which is going to be the most common thing, whether they're AGMs or gels or flooded, you can only use 80% of the capacity of that battery is useful. It's kind of like if you think about your flashlight. Eventually the batteries get drained so much that even though you can see that the bulb is lit, you can't see where you're walking. So that last 20% is just so low in voltage, it's just not really usable. So the first thing to do is to take the rated battery capacity in amp hours, and we typically use the 20-hour capacity rate for calculations, and multiply that by 0.8 or divide by 80% to get the actual usable amp hours. And then once you have that, you can multiply that by the voltage of the battery, and best to use the nominal voltage, either 12, 24, or 48, and that gives you the watt-hour figure. It'll give you actual watt hours, and of course, if it's over 1,000, you can convert that to kilowatt hours.
All right. The next question, what is the best choice for an off-grid application where the temperatures go below -40 degrees Fahrenheit?
That's a tough situation. Flooded lead-acid batteries will freeze, obviously. I'm sure people have this problem with their automotive batteries. It's really the same technology, although slightly different designs, a starting battery rather than a stationary deep cycle battery. Most batteries have much reduced capacity, much greater losses of capacity at low temperatures because it's a chemical cell. There's a chemical reaction happening in the battery that produces the electricity. As the battery is colder, the chemical reaction happens at a slower rate, so you do have reduced capacity, reduced charge and discharge capabilities. -40 is pretty tough. Gel cells say that they're rated down to about -75 Fahrenheit. But if the rate they have virtually, and even most of these batteries at -40 are going to have virtually no capacity, or very low percentage of capacity. The only thing I can really recommend is to have some form of keeping the batteries warmer at that temperature. I've seen a lot of systems in northern climates have buried battery boxes, sometimes using things like concrete septic tanks or other things, some sort of controlled room. I mean, actually, even if you have it in a room that's insulated and maybe has some windows in it, let some sunlight in, that'll actually let some heat into the room. Batteries are very dense, so it takes them a long time to absorb heat, but also a long time to lose their heat. So typically, if you get any kind of heating in a room, you can keep a battery above its lower point. About the only thing you can really do is I would recommend a sealed battery because they're less prone to freezing, either an AGM or a gel, and you just have to greatly size the battery much larger because of the lower capacity at the low temperatures. Years ago, mountaintop in northern Quebec, Canada, and we actually had to size the battery 8 times its rating just because of the low temperature performance. So yeah, low temperatures are certainly an issue. There's not a whole lot of ways around that. Obviously, any kind of electrical heating is just using energy that you're trying to store in the batteries. That's not really going to work. Propane heating might be a way to go, or some other form of trying to keep the battery temperature up, not only to keep them from freezing, but to actually have some usable capacity in them.
All right, great. Thanks, Brian. The next question we have, what is the recommended method of determining capacity or condition of lithium-ion batteries?
Well, many lithium-ion batteries have battery management units in them that actually keep track of the cycles and the cycle life, so you can get information through a monitoring system there. Other batteries that may not have that kind of sophistication, there's really not a lot of ways to measure it. I mean, you could certainly just keep track of your cycles and your cycle life, but without actually having monitoring. They're sealed, so you can't use a hydrometer to test the electrolyte or something like that. So it's really all about monitoring systems to be able to keep track of that at that point. As they age, there will be some loss in voltage, so that may be an indicator. But really having a monitoring system is really about the only way to keep track of that.
All right. And if an AGM battery bank becomes partially sulfated due to lack of full charge regularly, can anything be done to regain capacity?
Good question. Some of the manufacturers do have a process of equalization. It has to be a very tightly controlled equalization and not get too much, but yeah. Some of them, and it varies by manufacturer, so I would certainly check in a particular battery manufacturer. But it is possible to do some equalization on sealed batteries. It's much more limited than what you can do with a flooded battery. Yeah, that's one of the disadvantages of sealed batteries, that they're just not as forgiving of not only overcharge but also undercharging and sulfating up. There's not a whole lot you can do. I would certainly check with the manuals and the instructions for a particular battery that you have. Some of them recommend the equalizing charges, and some don't. And it really varies by the manufacturer. It's just not a whole lot you can do there. And maybe still one of the reasons why flooded batteries are still preferred by a lot of users and installers is that they are really much more forgiving in that way.
Okay. And have you heard anything about the Sony battery?
Sony. I think Sony is one of the companies that are making the lithium batteries in the smaller cells that are used in compound numbers for electric vehicles. Other than that, I'm not familiar with anything else that Sony is working on, but it certainly wouldn't surprise me if they're working on different battery technologies. They're a pretty innovative company, and there's a lot of work going on energy storage right now.
All right. And the next question we have, how does using tap water versus distilled water affect battery life on lead-acid units?
Another good question. Well, as I said earlier, a battery is an electrochemical cell. There's a chemical process going on in there, and it's that chemical process that produces an electron flow and produces energy, produces usable power to be drawn from the battery. If you introduce a lot of minerals or contaminants into the electrolyte, you're going to cause different battery chemistry reactions that are going to reduce the capability of the battery. It can actually do so fairly quickly. for instance, if you have a lot of dissolved calcium in your water, that'll greatly affect a lead-acid battery, so I certainly wouldn't use that water. You really just want to use distilled water or deionized water. Either way, it's a type of water. Reverse osmosis will do this too. It actually removes the mineral because you just don't want to have a chemical process in there. Iron is particularly a bad thing to put in batteries. Calcium can be dangerous for batteries too in terms of their lifespan. So distilled water only. And this is sometimes a problem in remote parts of the world is actually getting access to distilled water, and maybe a good reason to use sealed batteries in that location.
All right, thanks, Brian. Next question we have, does the Tesla Powerwall require an inverter in addition to the Tesla unit?
Yes. Yeah, the battery is, the Tesla Powerwall is just a battery. It does have electronics in it to operate the battery itself, cooling and heating system and battery management system and all kinds of safety devices. It's a pretty sophisticated device, actually. But all it's doing is storing energy. It's not processing that into either charging or discharging. It's not producing AC. It's meant to be used as storage, to be used with an inverter to produce AC power. So yeah, you definitely need inverter and other components to be in the system. Not all of this is fully fleshed out with Tesla yet. They're still working on some of the infrastructure. But right now they do have operating systems using the Solar Edge inverters and Solar Edge optimizers on PV arrays.
All right. And have you heard anything about the new M-phase batteries?
Only that they're working on one. I'm not privy to all their fine internal details, but I understand they're working on technology. I don't have any details that I can give out, but that is something coming down the pike. Enphase also has their battery system that they're working on. Solar Edge has the system. I think in the next 5 years we're going to see enormous innovation in battery technologies and in battery applications, particularly going for small scale, not only for backup systems but also for things like load shifting and peak energy, peak reduction, and that kind of stuff. So a larger part of people's utility bills are being done on peak energy consumptions or time of use or other things than just straight kilowatt hours. And I think batteries are going to be a big help in smoothing out people's electric bills for that. Of course, you have to look at the cost of the battery itself compared to the cost of those peak charges or those time of use charges to see if the economics pencils out. But I think we're going to see a lot of that. And we may even see more situations of as more and more people have electric vehicles parked in their driveway or in their garage, that battery pack in that electric vehicle may be a viable option for use as backup systems. So maybe you plug your car into your house and it operates as a backup system. Obviously, you wouldn't want to drain your car battery all the way, so you're going to be limited in how much power you can draw from that. But there's a whole system being worked on, maybe more in Europe than here, called vehicle to grid. And the idea is that you could have millions of electric vehicles that are plugged into the grid and use that highly distributed energy storage device. So there's a lot of thinking going on with that. There's nothing particularly on the market yet for that, but I think we'll see that in the future. Again, there's a lot of innovation going on in the battery field, which is one of the reasons we wanted to do this presentation.
All right, and we have a few follow-up questions about distilled water. So what about highly filtered rainwater or water that comes from an air conditioner system?
Well, I would imagine the air conditioner would probably be cleaner water because that's just a condensate. But, the funny thing about water is in order for it to go from a vapor form to a liquid form, it actually has to coalesce around a particle. So rainwater, every drop of rainwater has at least one particle in it. And actually, they recently found out that a lot of rainwater has what they call micrometeors. These are actually tiny, tiny little microscopic meteors entering from outer space that hit the clouds and form droplets of water, which they've rainwater is not really that clean chemically. It may be fine to drink, for instance, but as a chemical, it's not really very good. And you really can't filter that out with filters that make any sense. Reverse osmosis is pretty clean, but just direct use of rainwater or air conditioning condensate water is not really going to be clean enough for a battery. Now, I would certainly say that both of them are probably better than most tap water is, or certainly pond or well water is, but I wouldn't recommend using it. Really distilled water or deionized water is really the way to go.
All right, and can you comment on tubular plate batteries?
Yeah, I didn't really add that to the presentation, but that would actually be a good thing to add. There's a number of companies that have produced tubular plate. Most lead-acid batteries are done with what they call flat plates, and it's a combination of flat plates, typically in a vertical arrangement. The plates are different materials in them, very commonly either calcium or antimony. And there are some manufacturers that are making plates that are tubes rather than flat plates. They seem to have longer cycle life. They're able to have higher discharges and charge rates. They tend to have less loss of active material. Battery plates will slough off some active material over the years. There's typically some room left at the bottom of the battery to accumulate this sloughed off material, but that material is not available for energy conversion. So the tubular plates do seem to have some advantages. They're more expensive to manufacture. Fewer manufacturers are doing it, but they're actually a rather interesting design that does have a higher cycle life and a higher total years of life than typical flat plate batteries. We don't carry any of those at this current moment, but we're looking into bringing some in, actually.
Okay, and have you had any experience with lithionic batteries?
Lithionic batteries, I'm not really familiar with the term, but I'm sure it's one of the many lithium ion forums that are out there. I don't have any direct experience with those, no.
Okay, and do you have any information on, let's see, vanadium ion batteries?
No, I've heard of them. That's another in the laboratory thing they're working on. It's just everyone's looking for different technologies to patent. One of the big advantages of lithium is it's lightweight, and that's really important in mobile applications and in electric vehicles. Not nearly as important for stationary applications. So even though I think most of the innovation and most of the research work is being done with lithium, there are certainly other materials that are being looked at. The Aquion battery is out of that idea that weight and size restrictions are not necessarily a big factor in stationary batteries. The vanadium batteries, I don't know much about them, but I have seen that there's some research going on in that.
All right. Do larger nickel cells exhibit the black negative wire contamination of smaller cells?
No, they don't seem to have that problem. I think that is a problem with the smaller cells, but the larger ones don't seem to have that problem along. Thomas Edison was working with nickel iron cells over 100 years ago, and there really hasn't been a whole lot of change in them. So they have really a lot of history of use, and there really haven't been any problems like that. They really do last for decades.
All right. And a question on the Outback nanocarbon batteries.
Yeah.
I see it recommends cycling between 30 and 80%. Can this be controlled via absorb time, or what other ways are there to try and keep the battery in that 30 to 80% range?
Well, I assume we're talking with an off-grid system here. Typically with backup systems, people aren't really worried about the range. They just want the lights to stay on. But in an off-grid situation where you are cycling it either every day or on a very regular basis, you do want to keep track of that. There's no real automated systems for that I know of. Certainly there are things like low voltage disconnects and whatnot, but not actually something that's going to maintain the battery in that range. That is the most efficient range, but you still want to, even with any lead-acid battery, you still want to get up to 100% charge on a regular basis. You just don't want to discharge them too much every day. We typically recommend not more than a 50% discharge on lead-acid batteries on a regular basis. You can certainly go down to 80 on an emergency basis, or very low light situation, but you really want to keep your cycles above the 50% mark. And actually, if you're working really more in the 20, 25, 30% life. So that's really where that comes from, is from the efficiency standpoint, because the last 10% of battery capacity when you're charging the battery, like between 90 and 100% depth of discharge, there's typically a lot of energy lost just in heat and in bubbling of the water. It's electrolysis of the water, which is splitting into hydrogen and oxygen. So this energy is consumed, but it's not consumed as some form that we can then use to produce energy later on. So it's kind of wasted energy. So that's where that 60 up to 20% charge rate is most efficient on a battery, but you still want to fill it up to 100% on a regular basis to prevent sulfation and stratification from happening.
Great, thanks, Brian. Next question we have, does a gel battery have any significant advantage over an AGM battery?
Well, they typically have higher cycle life. That's really the big advantage there. They are a little more expensive, so for backup applications that aren't going to see a lot of cycles, they're not really are cycling a daily. They do tend to have longer cycle life. Although I have to say that modern AGM technology is catching up on that pretty well. It's like Outback's AGM discharge, daily depth of discharge. That's really good at what gel cells typically do. Gel cells are more expensive to manufacture, so as AGMs get better and better, we may actually see fewer of them available, fewer of the gels. But very regularly and use AGMs for stationary applications that are just for backup or cycled less often, is generally the rule of thumb.
All right, and since we are hitting the 10 o'clock mark here, Pacific time, and we will go over a little bit longer, but I just want to remind everyone who has to log off that you do need to complete that survey to receive the presentation, the NABCEP certificate, and the webinar-only special. Also, we'll be uploading this video to YouTube once we're wrapped up here, so you can view it again at a later time. All right, and Brian, there's just one more question
Sure.
we'd like to get to here. And for anyone who didn't get their question answered, we'll do our best to answer via email once the presentation is over. All right, here we go. Brian, since you're off-grid, would you like to share with us what battery you have in your installation and what your system has in it?
Sure, I'd be glad to. I've been off-grid for over 30 years now, and although not always at this particular location, so a lot of the my power system is really pretty antiquated. I still have a set of ARCO 16-2000 PV modules that were made in 1982. 30-watt models, which were considered high power modules in those days. I still have decide that they need an off-grid test site and give me a really good deal on batteries. But I'm strongly thinking about using the Aquions, although I will probably settle on some lead acids that are maybe even a shorter life, like L16s, and wait for the technology to really fully develop. But I'm willing to try everything else too. I've also talked to Tesla about their commercial grade batteries for off-grid use, because the little Powerwall is not really large enough for off-grid house yet. So maybe something a little larger, and they're looking into that. I intend to experiment with as many battery technologies as I can. But right now I'm just using good old golf cart batteries. They're kind of an old technology. They're still fairly cheap to get, and they work quite well, and they last quite long. They typically last 5 or 6 years.
All right, thanks so much, Brian. That concludes our Q&A session of the webinar. Thank you so much for the presentation and all that good information.
Sure, I'm glad I left a good time for the questions, since there were a lot of them. They were great questions.
All right, so thank you everyone for joining us for our presentation, Battery Technologies. Next month, on May 13th, we have our next webinar in the monthly webinar series, and that topic will be grid tie energy storage, applications and solutions. So another really good one, very technical. We'll get into some really good stuff, so I wouldn't miss it. And you can check out our website for more training opportunities with AEE Solar. We've got a few workshops coming up, and always our monthly webinar. So have a great weekend, everyone, and thank you for doing business with AEE Solar.
Thanks, everyone.